video, we are going to talk about the different types of chemical bonds, which are ionic, covalent, and metallic. So 3 of them. This is going to be on page 6 of your packet. So pull that out and fill out the table as you follow along with this video. Okay, so a chemical bond is a force of attraction or an intramolecular force that is going to hold atoms together in a molecule or a compound. So you should already be familiar with the terms ionic and covalent because we learned about the differences in naming and writing the formulas for ionic and covalent substances. Okay, however, we're going to talk about how they actually form, and then we're also going to add in metallic bonds as well. So to start, we're going to go over ionic. So remember, for ionic compounds, that is going to be composed of a metal and a nonmetal. Okay, more specifically, it's going to be between a cation or a positive ion and an anion or a negative ion, because you got to remember that we have the polyatomic ions as well that can form ionic compounds. Okay, but for now, just think of it as a metal with a nonmetal. So ionic compounds are held together through ionic bonds, okay, which is our first type of chemical bond. And you want to think of it as a drastic trade of electrons. So picture metals as they want to get rid of the clutter, okay? They want to get rid of their valence electrons, whereas nonmetals are like electron hoarders, okay? They want to take as many electrons as they can. So this ionic bonds are formed by the transfer of electrons from a cation to an anion. So take this example of a sodium atom and a chlorine atom interacting with one another. So the sodium is a metal, and that sodium atom is going to lose its one valence electron and give it to this chlorine atom. Now the chlorine atom is going to gain that valence electron. Okay, when this happens, that sodium atom, because it's losing its valence electron, is thus going to become a sodium positive 1 ion. And the chlorine, which is gaining that electron, is then going to become a chlorine negative 1 ion. Okay, the sodium is going to be positive because it's losing a negatively charged particle, okay, making its overall charge positive 1. And that chlorine atom is going to be gaining one more negatively charged particle, or that electron, and thus having an overall negative charge. Because that sodium is a positive ion now, and then the chlorine is a negative ion now, that positive and that negative charge, those electrostatic forces, are going to strongly attract to one another. Okay, remember, positives and negatives attract towards one another. When they attract towards one another, they form this really strong ionic bond. Ionic compounds are going to typically look like this. So they're going to kind of have this like crystal looking shape. They're going to be like hard and brittle. All right, and that's due to the fact that ionic compounds have this crystal lattice structure. So that can be visualized through these models here. Okay, so this is an example of sodium chloride. So you can see how the sodium and the chlorine ions are kind of arranged in this highly ordered 3D, very symmetrical arrangement of repeating ions. Okay, so this is the form that ionic compounds are going to look like at the molecular level. So for melting point and boiling point, remember that the melting point is the temperature at which a substance is going to turn from a solid to a liquid or melt. And the boiling point is the temperature at which a substance is going to turn from a liquid to a gas, okay, or boil or evaporate. So ionic compounds are going to have high melting points and boiling points. So if we compare sodium chloride or table salt to water, the sodium chloride, being an ionic compound, has a melting point of 801 degrees Celsius and a boiling point of 1,413 degrees Celsius. Comparing that to a molecular or a covalent substance like water, H2O, which has a much lower melting point and boiling point. So just remember that ionic compounds are going to have really high melting points and boiling points. All right, and this is due to the fact that these ionic bonds that form are very, very, very strong. So in order for, say, a sodium ion and a chlorine ion to actually separate from each other, it's going to require a great amount of average kinetic energy, a really high temperature in order to do that, okay? Because the bond between them are super, super strong. Ionic compounds are good conductors, but they will only be good conductors or conduct electricity if they are melted, okay, or molten, or if they are dissolved in water, aka aqueous. Okay, they will not conduct electricity as solids. So if you look at this picture over here, this is just representing a solid sodium chloride lattice structure. So when it is in this lattice structure, it's really highly ordered, or you can say that the ions are localized. Okay, so this means that they are staying put. Okay, they can't really move around a lot. Okay, therefore, as a solid, ionic compounds cannot conduct electricity. However, if you were to take that salt, that sodium chloride, and dissolve it in water, eventually those ions, that crystal lattice structure, is going to break apart. Okay, so now when these ions are in, say, water, okay, or aqueous, they're delocalized, okay? They're free to move around, they're very mobile. When these charged particles are mobile or delocalized, this is the situation in which electricity can actually conduct through this substance, okay? So cannot conduct as a solid, but is a good conductor if it's liquefied or molten or aqueous, dissolved in water. The electronegativity difference between two atoms in an ionic bond is typically greater than 1.7. Okay, so it has a large electronegativity difference between the two atoms that make up that ionic bond. So, review: the electronegativity is the attraction for electrons in a chemical bond. So, how much these elements actually are pulling for those electrons and want those electrons. The electronegativity values for all your elements are on table S. So let's compare lithium and bromine and lithium bromide. So lithium has an electronegativity of 1 and bromine has an electronegativity of 3. So if we were to take the difference of the electronegativity values between these two atoms in this bond, 3 minus 1, that difference is a 2. That's greater than 1.7. Okay, same thing with sodium chloride. Sodium has a electronegativity of 0.1. Chlorine has an electronegativity of 3.2. Therefore, the difference is 2.3, which is greater than 1.7. Okay, so ionic compounds are going to have a greater electronegativity difference between those two atoms. That's greater than 1.7. And this makes sense because your nonmetals are typically going to have a higher electronegativity value. They want electrons more, right? Nonmetals gain electrons, they want them more. And your metals are going to have an electronegativity value that's a lot smaller, okay? They're more willing to give their electrons away, okay? They don't really have that strong of attraction for them, all right? So that difference in electronegativity between the metal and the nonmetal is going to be pretty high. All right, so here's just some examples of ionic compounds, which you should be familiar with already. Typically a metal and a nonmetal, more specifically a positive ion with a negative ion, because we can sometimes have a polyatomic ion that's on table E. But here we have sodium chloride, where sodium has a positive 1 charge and the chlorine has a negative 1 charge. Magnesium bromide, where magnesium has a positive 2 charge and bromine ions have a negative 1 charge. And then over here we have sodium nitrate. So this is an example when we can have a polyatomic ion in an ionic bond, where sodium is a positive 1 charge and the nitrate, if you looked it up on table E, has a negative 1 charge. Okay, so positives and negatives charged ions are attracted to one another, and they form this ionic bond because that metal is completely transferring one of its electrons to the nonmetal, causing this really strong electrostatic force of attraction between the two. Okay, next we have covalent, okay, which can also be referred to as molecular. So for covalent or molecular substances, this is when it's going to be composed of nonmetals only. Nonmetals only. Okay, and the bonds between these atoms are formed by the sharing of electrons between two nonmetals. Okay, so you can think of this as the nonmetals when they form bonds with one another. It's more of like a co-parenting situation. Okay, they're sharing the electrons. They're not completely losing or gaining any electrons, but rather they're just sharing them. Okay, between two nonmetals. So here are a few examples. So this is an example of what carbon dioxide would look like. Okay, carbon atom is sharing electrons with two oxygen atoms. Here we have an oxygen molecule, so diatomic oxygen, where the two oxygen atoms are sharing electrons between the two. And then lastly, down here, we have hydrogen chloride, or HCl, okay, where the electrons are being shared between the two. Okay, so for covalent, they're just the sharing of electrons between two nonmetals. So there are a bunch of different models that could represent covalent substances. This one over here is called a ball and stick model. Okay, so it just looks, the atoms will be represented by different colored spheres, and then the sticks represent those covalent bonds between them. So this is an example of methane. So methane is CH4. The carbon atom is in the center, whereas the hydrogens are forming, there's 4 covalent bonds, carbon hydrogen bonds that make up that molecule. We can also have a Lewis dot structure. So we've already learned how to draw Lewis dot structures for single atoms or ions. Okay, however, in the next few days, we'll learn how to actually be able to draw something like this. But this is also representing the covalent bonds between two oxygen atoms. Covalent bonds or substances that form covalent bonds are typically going to have a low melting and boiling point. So if we compare one of our ionic compounds, like our sodium chloride, has a really high melting point and boiling point, whereas something that's covalent, so something like sugar, so that's the chemical formulas here. It's made of carbons, hydrogens, oxygens, so nonmetals only. That has a much lower boiling point and melting point. Covalent compounds are poor conductors. Okay, if they're poor conductors, they cannot pass an electric current very well. Or heat. So we can also say that they're good insulators. Okay, so they insulate really well. Because covalent molecules or two atoms in a covalent bond are not formed by ions, they do not have charged particles, it's unable to carry an electric current. Electronegativity difference for between two atoms in a covalent bond is going to be less than 1.7. Okay, and this also makes sense because since it's between two nonmetals, both of their electronegativities are going to be relatively high. So the difference between the two is going to be lower. Okay, so less than 1.7. So for HCl, the electronegativity difference would be a 1. And then if we have a water molecule, let's say, which has an oxygen molecule in the center and then two OH bonds, so this would be a covalent bond here between the oxygen and hydrogen, and then we have a second covalent bond here between this hydrogen and oxygen. The electronegativity difference between oxygen and hydrogen is 1.2. Okay, so less than 1.7. Covalent or molecular formulas can be shown like here. So just remember, it's nonmetals only. So we have our water, H2O, we have methane, CH4, and then also any kind of diatomic molecule like O2. So the third type of chemical bond is metallic bonds. So metallic bonds will form between pure metals, okay? So where there's only one type of metal ion present. And the important thing to remember about the metallic bonds is that they have a mobile sea of electrons. So mobile means that the electrons are free to move kind of throughout the whole substance and move around all of the different positive metal ions. Okay, we can also, you might see the term mobile sea of electrons referred to as delocalized electrons. So this just means that they're not localized. They are not staying in the same place. The electrons are moving all throughout around those metal ions. Okay, so the model will typically look like this, where you have your metal ions and then shown are these moving electrons all throughout. Okay, mobile sea of electrons. Substances with the metallic bonds are also going to have high melting points and boiling points, okay, like ionic compounds. So if you compare the melting point and boiling point of a covalent substance like oxygen, which are very, very low, to the melting point and boiling point of pure gold. Pure gold melts at 1064 degrees Celsius and boils at 2800 degrees Celsius. So very, very, very high. Okay, you can also think of like when there's any kind of metal casting or steel casting or iron casting, where they have to melt the metal into a liquid. Okay, look how bright that is. Okay, this is extremely, extremely hot material. Okay, so in order for whatever this pure metal is, maybe it's gold. Okay, in order for that to melt, it would have to be at a super, super high temperature. Okay, so really, really high melting points and boiling points. Metallic substances are going to be good conductors, so they can conduct electricity as a solid or as a liquid, aqueous. So when they're molten, okay, like here, okay, when it's molten. But that's why all of our like copper wires and for phone chargers and things like that are made of pure metals, okay, because they can conduct an electric current, okay, due to the fact that they have that mobile sea of electrons. Okay, metallic bonds are not going to have an electronegativity difference, okay, because it's just one metal atom, okay, so they're going to have the same electronegativity, so there is no difference between them. Okay, so it might just say copper solid, gold solid, iron solid. Okay, it's just one atom, one type of metal.